Okay, so I'm going to explain conservation of energy and how that relates to rotational inertia. So if it's a closed system, meaning there are no external forces acting on something, then energy is conserved. This can mean that energy is converted into different types of energy, like potential energy to kinetic energy, but it has to be conserved. And so if we take the example problem from the AP test, which is, suppose that a spherical star spinning at an initial angular velocity suddenly collapses to half of its original radius without any loss of mass. Assume the star has a uniform density before and after the collapse. What will the angular velocity of the star be after the collapse? So we can solve this problem using the conservation of energy. We know that there's no reason for this energy to be converted into any sort of potential energy, because it's just not relevant to this problem. We know that its rotational kinetic energy will have to be conserved. So the equation for rotational kinetic energy is 1/2 of the rotational inertia, angular velocity squared, like this. That is equal to kinetic energy. So we know that the before and after kinetic energy has to be equal. So, but we don't really know the rotational inertia in this problem, so we're going to have to use the equation for that. But we do know that the rotational inertia of a solid sphere will be 2/5, I'm writing this down now, 2/5 of the mass times the radius squared, like that. So we can set up this problem. So 1/2 times 2/5. And the mass stays the same, so we can just use the variable m for that. And the radius, we'll just use r for the value of the original radius. So this, so 1/2 of the original rotational inertia times the original rotational velocity will be equal to, squared will be equal to 1/2 of the new rotational inertia, which will be equal to 2/5, same mass, so we'll just use that, and then r over 2 instead of just r squared times the new angular velocity. So this is what we have now. So now we're just going to simplify this and see what cancels out to see what our new angular velocity will be. So So now we have this little equation down here, and we can cancel some of this stuff out. Like the mass cancels out, r squared cancels out, and what we're left with, and we can just simplify out the fractions a little bit. So what we're left with is that the original rotational velocity squared is equal to 1/4 the new rotational velocity squared. So to get the new one, what we can do is multiply both sides of this equation by 4. So 4, and then square root both sides, and what we're left with is our new rotational velocity is equal to 2 times the old one, right? Like this. This is exactly what I did to get this. So in this problem, our answer would be D, which is 2 of the original angular velocity. Oh, and I realized I was saying rotational velocity all this time when I meant angular velocity, but close enough, I don't want to refilm this.